get started. So these are sort of the main topics of this week's reading. So we go through the normed dual of a normed space. So this is basically a stronger topology on the dual space than the weak star topology, which we covered last week. But we'll also sort of see how the two topologies are related. And then the second dual, which is the set of bounded linear functionals on the dual space. And then we'll talk about annihilators, which are probably familiar to most of us from other contexts like differential equations or whatever. But they come in handy here as well. And there's a way to sort of characterize the dual spaces and their quotients in terms of annihilators, which is interesting. And the annihilators are also handy in several of the proofs. And then we'll talk a little bit about duals of subspaces and quotient spaces. And then the next main topic is adjoints in terms of Banach spaces, which is very subtly different from sort of the standard adjoint from linear algebra and Hilbert spaces, and I'll get into that when we get to it. And then the main topic, I guess the main overall topic of this chapter that all this is leading up to is compact operators, which are Rudin has a good quote, which I'll show on one of the slides. These are basically some of the more nicely behaved operators on a Banach space, in that they behave more like operators on finite dimensional linear spaces than sort of other classes of operators on Banach spaces. So we'll talk more about that as well. Okay, so the focus in most of this chapter is on normed spaces, and most of the theorems, in fact, will require Banach spaces. There are a few that just are general linear algebra results or general topological vector space results, but most of them do use norms. So just a reminder of the notation from last time, this sort of script B from X to Y is the set of all bounded linear maps from X to Y. And since we're on norm spaces, which are metrizable, we recall continuous and bounded are the same thing. There is a vector space structure on this set of of linear maps. So it's addition of linear maps and scalar multiplication defined in the usual way. We'll show that we can use a natural norm, which is the operator norm, also probably familiar to most of us from other contexts that make BXY into a norm space. And then we'll focus in the second half of the chapter on the special case where, oh, sorry, no, this is the wrong bullet item for, I'll say that when I get to the actual bullet item. Yeah, I'm just saying in the special case where Y is the scalar field, when we simply have the dual space, we're mapping from X into the scalars. So the topology, as I mentioned in the previous slide, the topology that's induced by the operator norm will turn out to be stronger than the weak star topology, which we talked about last week. And we'll talk in the next couple of slides about that in more detail. And as I say in the italics here, a lot of the proofs in this chapter were quite long and took quite a bit of effort to hack through, although it was interesting and rewarding to do. And so I'm not going to prove too much in this presentation for two reasons. One is that it'll just be very, very long-winded to do so, and we'll sort of, more importantly, maybe miss the forest for the trees. I think it's kind of useful just to see what are all the main results without getting bogged down in the details. So I'll try to focus on that, and I'll put a few token proofs in as well. Okay, so first theorem, this is where we define the operator norm. The first one is the definition that Rudin gives, so it's the supremum of the norms of the image points of the operator when you apply it to the closed unit ball in X. I wrote down several equivalents. That's equivalent to the image under the open ball because of continuity, and it's also equal to the image of just the surface or the boundary of the unit ball, and that's just because things get bigger as you move from inside the ball out to its periphery. So you can restrict yourself to just looking at the points on the boundary. And then also, because of the last one, that's the third line says we can restrict ourselves to unit vectors. And so we have an alternate characterization on the fourth line where I take any arbitrary non-zero x and just normalize it by its magnitude to get a unit vector. So these four are all equivalent characterizations. I think Rudin tacitly uses all four at some point in the various parts of the chapter. There are other characterizations too in terms of infimums of like reciprocals and that sort of thing. But I'm not going to list all the different characterizations here. You can read more elsewhere if you're interested. So the main content of the theorem is that this does indeed give us a normed space, and also that if y is a Banach space, then so is bxy under this norm. So the Banach space being a complete norm space. Okay. So notation. I don't remember if he used this notation in the previous chapter, but we'll be using it sort of implicitly throughout this chapter. Elements of the dual space we'll just call like little x star will be a typical element. And then also this notation that he introduces, which is kind of nice. Instead of writing x star evaluated at x in the usual function notation, we introduce this notation that looks kind of like an inner product, where we put the input argument on the left and the functional to which it's being applied on the right. I mean, you could presumably do it the other way around as well, but that's the convention he chose. It's kind of nice because this notation ends up making it easier to think about the symmetry and duality between the various spaces, especially when you go to the double dual. And it also is very nicely compatible with the notation that he chose for the left and right annihilators, which we'll get to in a little bit. I just made a note here. This is different from an inner product for a couple of reasons. First of all, x and x star are not elements of the same space, so it's certainly not an inner product. But also, it's not conjugate linear in its second argument. It's linear in both. And that's, again, I guess it's not only a Rudin convention. I guess that's the standard Banach space convention. Whereas if this were a Hilbert space, you'd be having conjugate linearity in the second argument. So, and that's going to have ramifications when he defines the adjoint a little bit later. There'll be like a lack of a complex conjugate that would normally be there in linear algebra. But I'll go into that when we get there. So yeah, linear in both arguments, and there's no conjugation. Okay, so the next theorem, we have a different. Wait, did I? Yeah. Okay. So yeah, this is just a restatement of what the operator norm is in terms of the dual space. When we specialize the dual space, the name of the operator is something like x star instead of lambda, and then we're taking a supremum. And here I'm using the different notation for the function evaluation. So it's just x star evaluated to x. And since we're in the scalar field, these are just normal absolute values instead of a norm notation. And then for all x in the closed unit ball, so that's that first definition for the operator norm. So just restated it, but in terms of the new terminology. So as mentioned in theorem 4.1, this makes x star into a Banach space, and in this context and with that topology and that norm, Rudin calls this the normed dual, and that's as distinct from x star with its weak star topology, which is the weakest topology that makes all of these functionals continuous. And then we have this interesting duality. So we can, with almost the same expression, we can recover back the norm of the original x, given the elements of the dual space. So we take the supremum over the same objects, x star evaluated x, but we range, instead of over x, we range over x star in the closed unit ball of the dual space, and that gives us back the original x. So that's what gives us this sort of duality between the spaces. And as a result, we have a Well, first of all, if we consider the map from an element of the dual space to its evaluation at a point x, that's obviously a linear functional. The line above shows that it's bounded. In fact, the norm is x. Is the norm of x itself. And the other statement of the theorem is that the unit ball of B star is compact in the weak star topology. In there, so as I was saying, the map that we were just talking about on this in the last line of part B, this map that goes from the dual space to its evaluation at x. If we defined the weak star topology such that it was the minimal topology that makes all of those maps continuous, and of course we just said under the operator norm, these maps are also bounded, hence continuous. So that shows that this topology, the norm topology, is stronger than the weak star topology. All these functionals are continuous in the norm topology as well. And by default, the notation capital X star is going to refer to the norm dual as opposed to the same space with its weak star topology. But the weak star topology pops up a lot throughout the chapter as well, in terms of how these two topologies relate. Okay, then here's one where I've given a token proof because this one's pretty straightforward. This is just a different characterization of the operator norm. We can form this. We can take an element of the dual space of y and evaluate it at lambda of x. Okay, and then that's going to give me, well, lambda of x is an element of y, so we're applying y star to an element of y, so we get back a scalar. And so this notation makes sense. And then if we take the supremum over all x's in the closed unit ball of x, and overall y stars in the closed unit ball of capital Y star, and I lost my closing brace, then that actually gives us the sup norm, the operator norm for lambda. And this actually turns out to be quite a simple proof, so I went ahead and wrote it down here. Recall that from part B of this theorem that we were able to recover the original norm on X from the elements of the dual space. So we're using that on the first line here. We're saying that the norm of Y can be recovered from the dual space elements Y star in the unit ball in the dual space of Y. And then we can evaluate that at lambda of X, Y equals lambda of X, and I just plugged it in on this line. And then we apply, well, what does it mean? On the next line, I say, well, remind you, well, what is the norm of lambda in terms of its original definition? It's the supremum of all the lambda of x's normed for the unit ball within X. And then I just plug in what we had above. And so we end up with, I plug in this guy for lambda of X. And so we have a double supremum of these elements Y star evaluated at lambda X. And it's now taken over both norm of X less than or equal to 1 and norm of Y star less than or equal to 1. So it's pretty simple. Okay, so now let's talk about the second dual. So we have X star and we've normed it. So we now have the normed dual, and that is also a Banach space, as we said in 4.1a. And so therefore we can do this again. It has its own normed dual, and we can call it X double star. So 4.3b, which we'll scroll back very briefly to. This was again this last statement here, that the map from a dual space element to its evaluation at a point X is a bounded linear functional on X star and has norm of the original X. So because of that, we can give that mapping a name. Let's just call it phi of X. So it says that there is a unique element of the double dual such that X star evaluated X is the same as this element of the double dual evaluated at X star. So we may as well take this to the defining property of this phi without ever explicitly writing down what is its definition. Since there exists and is unique such a phi that has this property, we may as well just say, well, that's the only property we really care about anyway. And so call that the definition in our minds. And also, because the norms are equal, we get back this norm of X. That means that phi of X has a norm equal to X itself, which says that phi is an isometry. And of course, it's also linear, and therefore it's an isometric isomorphism onto its image. Its image may be a proper subspace of the double dual, but it is a closed subspace. And we generally prefer closed subspaces throughout this chapter and the last because most of the theorems related to subspaces require closedness in order to work. And because of this isometric embedding of phi of X into X double star, we can, and I'm sorry, of X really into X double star via phi, we can just identify X with its image under phi and pretend that X is a subspace of X double star. And so when we want to evaluate with an element of the double dual, this bracket notation is going to come in handy because we'll just switch sides. The first dual goes on the right side, and the second dual will be over on the left side, as represented as an X. And so mention again here the members of this possibly proper subspace of the double dual are exactly the linear functionals on X star that are continuous relative to its weak star topology. In other words, they're the ones that we used to generate the weak star topology. And as mentioned a couple of times, the norm topology is stronger, and typically the weak star topology is properly weaker than the norm topology. However, there are spaces. Rudin doesn't, I think, prove this, but he mentions it, and maybe it was in one of the problems that I didn't do. That some spaces like LP spaces, we actually do have this the fact that the image of phi is the entire double dual. So these are called reflexive spaces. So every element of the double dual is manifested in this way. So you can basically think of X as being isomorphic to X double dual in these spaces. So that basically is similar. That's familiar from finite dimensional linear algebra as well. The double dual basically is the original space. Okay, so let's talk a bit about annihilators. So here we have a Banach space, and we just have any subspaces. In fact, these don't even have to be subspaces. These could be just any subset of X, and these definitions make sense. But here we're assuming M and N are subspaces, not necessarily closed. We define two annihilators. So M is a subspace of X, and N is a subspace of the dual space. So for subspaces of the original space, we have this right perp notation. And that is meant to reflect that we are taking elements of X and applying stuff on the right in this bracket notation. So we're looking at all the right elements, which are the X stars in the dual space, that map all of the elements of M to 0. So as I say in words, it's a set of all bounded linear functionals on X that vanish on M or annihilate M. And then on the other hand, for elements of the dual space, we have the same requirement. We want X star comma X to be 0, but here we're going to vary over X instead of varying over, we're varying over X, and they have to have this property for all X star in the end. So this is, again, this sort of duality. So this is the subset of X that gets annihilated by every member of N. Both of these are vector spaces, and I believe that's true regardless of whether M and N are even subspaces. Just any set, they're still going to give you subspaces. As Rudin observes, the right annihilator of a subspace of X, that is the intersection of all the null spaces of these functionals as phi of x as x ranges over M. So null spaces of functionals are closed, and we're taking an intersection of closed sets, and so we get a closed result. And it's weak star closed in X star because these phi x's are the closedness of these things is under the weak star topology. And then on the other hand, the left annihilator of a subspace of the dual space, that's the intersection of just the null spaces of X star in N. Null spaces again are closed, and this is closed under the norm topology. And so then perp N is going to be norm closed in X. Okay, and then this theorem tells us kind of how a little bit of interplay between the right and left sides. So if we start with a subspace of X and we look at its right annihilator, so that's the set of all the dual space elements that that annihilate M. So then we get a set of dual space elements, so we can talk about the left perp of that guy. That turns out to be the norm closure of M in X. And so if M itself was norm closed already, then M equals this M right perp, left perp. So it is its own annihilator of its own annihilator, is how Rudin puts it. And then the same thing works in the other direction, except now we're working with weak star closure. If you take a subspace of the dual space and you take its left perp followed by its right perp, you get the weak closure of N, weak star closure of N. And so every weak star closed subspace is going to be the annihilator of its annihilator.
I find this to be pretty
so go through
interesting
a little bit of
because in like Hilbert spaces where this definition, at least like M with the transpose, just means orthogonal elements with respect to the inner product. We also get like this same property that if you take like the orthogonal twice, you get the closure of M.
Yes. These annihilators are sort of like giving us a proxy for orthogonality, right? We don't have an inner product, but annihilation by a linear functional is kind of analogous, I guess, to at least in the dual sense, it's analogous to orthogonality, which is kind of cool.
I see. Yeah, that makes sense.
That's kind of sort of how I've worked through it in my mind. Anyway, I haven't really made that like a formal notion, but yeah, I agree. It has a very similar feeling to how inner products work in Hilbert space, and I'm sure it's no accident that they chose the notation with the angle brackets, which I found a little bit weird at first, but after I understood sort of how everything plays, it makes sense that they chose this notation. Okay, so this is a recollection from way back in chapter 1. We defined on the quotient space. We defined a quotient norm. I had actually forgotten about this definition, so I had to go back and refresh my memory. So the way you define this quotient norm is you take given an x in the original space, you apply this quotient map pi, which just gives you the coset containing x. That's an element of x mod m, and then you take. We're going to define a norm on the quotient space by taking the original x and then forming the difference with all elements of M, looking at their norms, and then taking the inf. And this turns out to be well defined and gives you a something which is indeed a norm. That was theorem 1.41. Okay, so why did I bring that up? Well, because we are now going to relate how the norm on how the norm duals are related on these spaces. So M star, which is the quotient, the dual space of this closed subspace, that that's has a under its norm dual. It's basically equal to, although it's really isomorphic to, it's basically equal to the quotient space of the dual of the original X by the right perp of M. So this is kind of interesting. You don't really there's nothing really new to be gained by thinking about the topology, I guess, of the dual of M. You can basically get it entirely based on knowing the norm topology on X and modding by the annihilator of M, and then just applying the normal quotient norm, and then that gives you this M star with the same norm. And then the sort of dual version of this is if we take the quotient space X mod M and then take its dual, that's isomorphic to the right annihilators of M. So as mentioned at the last sentence here, these are technically isometric isomorphisms, not equalities, but in most cases it's probably fine to just think of them as equalities. And then he gives a theorem that gives us a more technical statement, which is useful when you want to actually prove it, but it's not really that pleasant to read, and it's kind of confusing to read. So I prefer to just remember that there is an isometric isomorphism between these pairs of spaces, and not necessarily worry about how do you write it down, because you don't usually need to write it down except when you're proving that it exists, at least as far as I can tell so far. Typo, that should have been of A. I'll try to fix that before I send the slides. Okay, so then on to the next main topic. This is adjoints. So given an operator that's in BXY, so these are the set of bounded operators or continuous operators, we can define an adjoint on the space of operators from Y star back to X star, and we'll call it T star, and we'll see how it relates to T. So this is analogous to, in finite dimensions, all of this is analogous to basically transposes, not conjugate transposes in this case, because we're not having any conjugates on our fake inner product. And so this T star is going to turn out to be, in finite dimensions, is going to turn out to be equivalent to just the transpose of the original matrix of T, not the conjugate transpose. Whereas I think the usual definition of adjoint in linear algebra, it would have the conjugate in there, because they're dealing with at least when they're dealing with spaces that have inner products. I think that's where I've typically seen it defined anyway. Have you seen it any differently, James?
I don't recall necessarily.
Yeah, I was a little confused at first, because like some of the theorems were saying like the T and T star had the same eigenvalues, and like, wait a minute, well, aren't they conjugates of each other? And then I went back and reread the definition and realized, oh yeah, it's because we don't have conjugation on the angle bracket here is why the difference. But anyway, that's one thing to keep in mind. And apparently that's not just a Rudin quirk. It's fairly standard when talking about Banach spaces that the adjoint is defined this way. And so it's a little funky because like Hilbert spaces are also Banach spaces, and Hilbert spaces have adjoints which do have the conjugate definition. So I don't know, when you think about them as Hilbert spaces, you use the conjugate definition, and when you think of them as Banach spaces, maybe you don't. Anyway, slightly
I
confusing,
think
but I cleared it up in my mind.
there seems to be like a big, at least you need to differentiate between Hilbert spaces and
Yeah.
general Banach spaces, because
Yes.
a lot of things just don't move on to like Hilbert space conventions
Yes.
here.
Yes. That's right. Like, I'm sure that's why they defined it this way. But there is a funk that it is going to be slightly confusing if you're dealing with a space like L2. You got to think about which adjoint are you talking about. But anyway, just something to keep in mind. There's a theorem that gives us the existence and uniqueness of this adjoint, and it's worthwhile to go through once. But similar to the statement about the double dual, it's I always just think of this as the definition of the adjoint, and because that's all you really need is how it behaves. You don't really care how you define it typically, at least in most linear algebra applications. So I always just think, okay, T star um, is the unique linear map that when you move from Tx comma Y star, you can move the T over and then you put a star on it, right? That's how we always think about it in linear algebra as well. And then the other statement of the theorem is that T star and T have the same operator norms. So it's interesting to go through this proof, and it takes a little bit more work since we now have topologies to deal with, and need to make sure to dot all the I's and cross all the T's. So it's slightly more complicated than like the linear algebra version, but it all works out fine. And again, just use the result. Just a reminder of the notation here. For any operator in BXY, the null space is going to be this sort of math cal n of t. It's a set of all elements that get mapped by t into 0. And then Rudin likes to use the word range and math cal r. I usually call it image, but whatever. It's a set of all points in y that are mapped to by t for some x and x. Usual definitions. And then we have some theorems about how the null spaces and ranges of of T and T star are related. So the null space of the adjoint of T is the same as the right perp of the range of T, which again kind of gives you that flavor, right? The null space is stuff that gets mapped to 0. This right perp is stuff that gets mapped to 0. It's not quite orthogonality, but it's why the annihilator comes in handy when dealing with linear functional, just kind of playing the role of null space-ish kind of things. And then the null space of the original T is equal to the left perp of the range of T star. And again, this is a bit of work to go through and prove all this stuff, but remembering the properties is pretty easy, and it is useful. It's used throughout most of the remaining proofs in the chapter. These characterizations. Actually, no, I take it back. These are actually pretty easy. It's 413 that's hard. Yeah, 412 is pretty easy. So in fact, this is another proof. I'll just go through right now because it's quite simple. So why is the null space of the dual equal to of the adjoint equal to the right perp of the range of T? Well, if we have a Y star that is in remember T star is mapping Y star back to X star, so elements of its null space look like Y star. Then by definition, T star Y star is 0. Putting that into function evaluation form, remember T star Y star is an element of the dual space of X, so it's a functional. Calling it equal to 0 means that if you apply it to any value in X, you get back 0. It's the definition of a function being equal to 0. And then we use the property of the adjoint that if I can slide it over to the other side and remove the star in this case, we get T x comma Y star equals 0 for all X. And what does that mean? That means that Y star annihilates all the TXs. And what are the TXs? They're just the range of T. And to say that Y star annihilates them says it's in the perp. So that's all that is. So the notation can be a bit confusing, but the facts are really simple. And then the second one is quite similar. If we have an X that's in the null space of T, that means Tx equals 0. And that means that if I take any Y star and evaluate it at Tx, of course I get 0. And this is an if and only if, because Y star separates points. So the fact that Y star evaluated at all the Tx's gives you back 0 implies that Tx equals 0. Sorry, that all Y stars evaluated at Tx gives you back 0 means that Tx must be 0 because Y star separates points. And then on the next line, we just again move the T over to the other side and put a star on it, and same qualifications otherwise. And now what does this mean? X is something that gets annihilated by all of the T star Y stars. So X is a thing that gets annihilated, so it's in a perp of, and And what is all the set of all the T star Y stars? That's just a range of T star because we're letting Y star range over all the capital Y stars. So again, just unrolling the notation to see what it means, and it's all pretty simple. Okay, so then this theorem was fun. This took I think James was mentioning before we started the presentation. This one was a pretty long proof. And going through all the
Yeah, this
details
one was
is
rough.
fun and kind of challenging. because he's I noticed Rudin has definitely been dialing up the level of like how much he omits from in terms of details in this chapter. So filling in the details takes a little bit more work in this chapter, but it was really useful and rewarding to do it. Highly recommended. So this in the red title bar here, I've called this closed range theorem. So as Rudin points out, this theorem and the next couple are often sort of loosely grouped together and called the collection of closed range theorems. The next one will make it clearer why that name applies. But anyway, if we have we let U and V be the open unit balls in two Banach spaces X and Y, and T is bounded operator from X to Y, then we get A implies B implies C implies D, and then finally D also applies A for some delta. I forgot to mention in the hypotheses, we're given a delta greater than 0 as well. So then given that, for that delta, A implies B implies C implies D, and then D will imply that A holds for some delta, and so then the cycle continues. Not going to go through this proof. This one was pretty tough. It sort of feels a little open mapping theorem-ish, right? It's saying like, well, look, the image of the unit ball under T contains some scaled version of an open ball, right? And also the range of T of X is going to be surjective. But I still haven't quite wrapped my brain fully around all the ramifications, even though this theorem does get used several times in the other remaining proofs in this chapter. I still haven't really given myself a good intuitive feeling for this theorem. Were either of you guys able to sort of come up with a good sort of succinct way to remember all this?
Not yet, unfortunately. I did feel it's a
Yeah.
bit open mapping. I think even like the proof was in the spirit of the open mapping in a way.
Yes, indeed. Yep.
But yeah, it
Yeah, but
still
I haven't
needs some
really
time to click.
I haven't really sort of like massaged it into my brain yet. But yeah, it may probably become clearer when it gets applied in future chapters, I imagine. Okay, so anyway, that's a big set of technical results, and it may also have a sort of more intuitive feeling, and it definitely gets used a lot in the rest of the proofs in this chapter. One of the ramifications, and this is sort of, I guess, why we're calling it these things the closed range theorems. With the same hypotheses, X and Y are Banach spaces, and T is a bounded operator between them. These three things are equivalent. So the range of T is closed in Y, and then we have two statements about the range of the adjoint of T in the dual space. The range of the adjoint is weak star closed in the dual space under the weak star topology, and also is norm closed in X star under the norm topology. So those three things are all equivalent if you have a bounded map from X to Y. And then we have another theorem which is similar with the same hypotheses. Range of T is all of Y. So in part A, we said, of the previous theorem, we said it's definitely closed in Y. If it happens to be all of Y, then well, I mean, part B says T star is going to be 1-to-1. So that's the new information. And R of T star is norm closed. We already knew that from part C, right? Because R of T being equal to Y certainly means it's going to be closed in Y. So A of the previous theorem holds. Therefore, C holds. So certainly R of T star is norm closed. But then going the other direction, if R of T star is norm closed, well, then we know that R of T is closed in Y from the previous theorem, but the new information is that if T star is also injective, then the range of T is not only closed in Y, but it's all of Y. So it's a little bit of a bit of a duality, and this I think if you think about the finite dimensional case, right? It's clear what they're extending here. Basically, if the transpose of the matrix is 1-to-1, then the original matrix is surjective, right? Just in terms of the either rank considerations or however else you want to think about it. So this is basically the infinite dimensional version of the same thing. And again, we require closedness of the various subspaces for everything to work. Okay, so on to the final main topic of the chapter. We're going to talk about compact operators. So what is a compact operator? Well, we're going to start with X and Y being Banach spaces. We're going to characterize it in terms of how T maps the open unit ball of X. So if T is a linear map from X to Y, and here the definition applies whether or not this is even a bounded operator, although, as you'll see, a consequence is that it is, in fact, bounded. Excuse me, the definition is that the image of the excuse me, swallowed coffee the wrong way. The ramification is that the definition is that if the image of the open unit ball and you take its closure, if that is compact in Y, then that's the definition of T being a compact operator. Um, Now, of course, if the closure of T of U is compact in Y, then it's also going to be bounded, right? You can just cover it by balls of like radius n, and you only need finitely many of them, so it's going to be bounded, and therefore T is mapping the open unit ball into a bounded set, and so therefore T is actually a bounded operator, even though we didn't assume that initially. Moreover, Y is complete, and it's a metric space, so we have a couple of characterizations that are useful throughout the whole rest of the chapter. In a metric space, compact is equivalent to complete and totally bounded. We may recall from topology. So if we're in a complete metric space, then subsets whose closure are compact are exactly the ones that are totally bounded. So an alternate characterization is that an operator from X to Y is compact if and only if its image is totally bounded. And then also in the metric space, we have the characterization that compact and sequentially compact are the same thing, and this doesn't even require completeness. And what does this mean? T is compact if and only if every bounded sequence in X has a subsequence such that the image of that subsequence is convergent to a point in Y. And we'll use that in a number of the proofs, and I have an example at the end where I'm going to use this as well. So keep that in mind. And then I thought was a good quote, so I've highlighted it. Like, why do we care about these compact operators? Rudin says they're in some respects as similar to linear operators on finite dimensional spaces as you have any right to expect, given that you're in an infinite dimensional space. So they behave basically as nicely as you can hope for. So that's one reason why people focus on them. And I guess a fair number of important operators in like PDEs turn out to be compact anyway. So they're useful because they have concrete applications as well. Okay, so this is just a reminder of some notation. So we're going to specialize now and look at operators from X to X. So in that case, we can apply an operator repeatedly. Just a reminder that B of X is now a Banach algebra, so the quote-unquote multiplication is just the composition of functions. So S of T is defined as the product of S of T, and its definition is that you evaluate first T and then S. And then the usual proof goes through that the norm of ST is less than or equal to the norm of S times the norm of T, which shows that ST is also bounded, so it's in fact in B of X. And then you can define powers the usual way. If you have T as an operator, its zeroth power is just defined as the identity map. First power is defined as T itself, and then in general, the nth power is T times the previous power. And then a little bit more in terms of definitions. In a Banach space, we're going to say that an operator in B of x is invertible if there is an element of B of x such that st equals I equals ts. So we're requiring S itself to be bounded. So doesn't suffice to just say a priori. It doesn't suffice to just say it's bijective. However, the open mapping theorem, as Rudin points out, actually does imply that it is sufficient to have bijectivity. So the null space of T will be the null space of T is 0 and the range of T is x. Then you are in fact invertible according to this definition. The inverse will be bounded as well. Okay, so why are we talking about B of x? Well, whenever we talk about B of x, we were going to be repeatedly applying things, and we're interested in eigenvalues and stuff, right? So let's talk about, there's slightly different notions in the infinite dimensional case between the spectrum and the set of eigenvalues. So let's walk through this. It's important to keep the distinction in mind. So the spectrum is the set of all scalars such that T minus lambda I is not invertible. And as Rudin points out, this can happen in one of two ways, right? If T minus lambda I is not invertible, then either it's not surjective or it's not injective or both. However, because we're not in finite dimensions, it's possible for only one of these to hold and not the other. So the range of T minus lambda I is not all of x, or T minus lambda I is not 1 to 1. And only in case 2 will we call lambda an eigenvalue. And that's because, well, if T minus lambda I is not 1 to 1, then there's some non-zero x such that Tx equals lambda x, and that corresponds to the usual definition of an eigenvalue-eigenvector pair. So we're interested in the eigenvalues are just the ones where 2 holds. So, and then the corresponding eigenspace is the null space of T minus lambda I, which is the set of all eigenvectors associated with lambda along with the 0 vector, which never gets to be an eigenvector in linear algebra. And in general, and we'll see an example of this, the set of eigenvalues is a proper subset of the spectrum. So in general, you can have lambdas for which T minus lambda I is 1 to 1, but the range is not all of x. We'll see for compact operators, however, the only special case is 0. So if the set of eigenvalues is a proper subset of the spectrum, the only thing that can be in the spectrum that's not an eigenvalue is 0. For non-compact operators, that's very far from true, and I have an example at the end of the presentation. 0, and by the way, let's think about 0. 0, we specialize into the case of lambda equals 0. The condition is simply either T itself is, the range of T itself is not all of x, or T itself is not 1 to 1. So in other words, T is either not injective or not surjective. And in infinite dimensions, we know that there are operators where one is true but not the other, right? So it's not surprising that 0 is kind of special, and it can be in sigma of T without being an eigenvalue. Okay, so we got a bunch of theorems, results rather, and this is another sort of long-ish theorem. C was by far the longest one to prove, and the proofs were kind of technical, and I didn't feel like super enlightening in terms of clarifying why the result is true, although it was illuminating to see how the earlier results get used to prove these results. But I prefer to just like remember these results rather than how they're proved, because it's not super obvious from the statements. So let's go through them. If T is a bounded map from X to Y and it has a finite dimensional image, that automatically makes T compact. So that's nice. And then going sort of the other way, if we have an operator that from X to Y that's known to be compact, and its range is closed, then its range has to be finite dimensional. C says the compact operators form a closed subspace of, sorry, I didn't mean to put T element, just of belt B x to y under the norm topology. And like one key, because the subspace, that means the somewhat non-obvious fact that the sum of two compact operators is compact, and maybe the more obvious fact that the scalar multiplication of a compact operator is compact, and they form a closed subspace. This is a pretty long and technical proof, but a cool result. And then specializing for the next three to the case where we're mapping from X to itself. If T is compact and lambda is not zero, then that means certainly the null space of T minus lambda I is non-trivial, right? That's the definition of, oh no, sorry. Yeah, no, we're not saying lambda is an eigenvalue here. We're just saying lambda is a scalar that's non-zero. Then it's always the case that the null space has finite dimension. And in the case where lambda is an eigenvalue, it'll have non-zero dimension as well. And then if we are in a case where X is infinite dimensional and T is a compact operator, then we're guaranteed that zero is in the spectrum, meaning that T is not going to be surjective. So a compact operator cannot be surjective onto an infinite dimensional space. And then finally, this gets used several times and is quite useful, actually. If you have two elements, S and T, that are bounded operators on X, and one of them is compact, then both of their products are also compact. So that's it's not super obvious that that's useful, but it definitely gets used in some of the theorems, and I'll also use it in an example at the end. This is a nice characterization as well. If T is compact, then so is its adjoint. So no degenerate weirdness there. And then we'll talk a little bit about complemented subspaces. This is quite similar to the definition in finite dimensional linear algebra, except here we require things to be closed subspaces. So, and here all this stuff applies to any topological vector space, although we're going to apply it in Banach spaces. So if M is a closed subspace of X, and there's another closed space of N of X, such that X is their sum and their intersection is trivial, then in the usual way we say this is a direct sum of M and N. X is a direct sum of M and N. And we say that M is complemented in X. It's complemented by N, and usual notation, M O plus N. And we have a couple of theorems for when things are complemented. In finite dimensions, there's always a complement available. In infinite dimensions, not quite so nice, but if M is finite dimensional and X is locally convex, which will certainly be true in Banach spaces, then M has a complement. And on the other hand, if the codimension, which is the dimension of the quotient space, is finite, then whether or not locally convex, M is complemented. So I think of this as if M is not too big, or if it's super big and not too small, then it has a complement. So either it's finite dimensional itself, or its codimension is finite dimensional. It's finite. Then it has a complement. The middle ground where both of those are infinite. Presumably it's not true, although I don't have a counterexample. There might have been one in the exercises, but I didn't have time to do them this week, so I'll have to get to those when I get a chance. Okay, and then this is a cool result, and this was also a pretty long proof, and this gets applied and will be sort of amplified a bit in the next theorem, which is sort of the big theorem in the chapter. But let's go through this one first. If X is a Banach space and T is an operator on Bx, and it's compact, then if we look at any set of eigenvalues that are staying away from zero, So basically, there's some R that's positive, such that they all have magnitude bigger than R. So they don't cluster at 0. Then for every lambda in that E, the range of t minus lambda I is not all of x, and E is finite, so there can only be finitely many such eigenvalues. So what does A say? A says that lambda is in the spectrum of T, right? That was the definition of the spectrum. And then B says there can only be finitely many. And by the way, if you consider the case where R is 1 over n, that says there's only finitely many eigenvalues bigger than 1 over n, and then take their union as n goes from 1 to infinity, that says that at most there could be countably many non-zero eigenvalues, which we'll mention again in the next proof. So that's a really cool result, and it was a lot of blood and sweat to prove it, but it was fun to go through, and the result is really nice. And then this is sort of the big theorem of the chapter, basically showing that compact operators behave a lot like finite dimensional operators. So if T is a compact operator on B of x and x of an Knox space, then for the non-zero scalars anyway, all four of these numbers are the same. So all right, what is alpha? Alpha is the dimension of the null space of T minus lambda I. So that's the eigenspace of lambda if lambda is an eigenvalue. And then sort of dually in one way, we have the quotient of x by the range of T minus lambda I. That dimension is the same as the dimension of the null space of T minus lambda I. And then when we look at the dual versions in terms of putting stars on everything, those pair of numbers are not only the same as each other, but they're also the same as the original alpha and beta. They're all equal and they're all finite for a compact operator. Moreover, for non-zero values of lambda, I mentioned this before, if you have a non-zero number that's in the spectrum, then it's also an eigenvalue, not only of T, but also of T star. And it's not lambda conjugate being an eigenvalue of T star, it's lambda itself because of the way we're defining the adjoint in Banach spaces. So 0 is the only guy that gets to be different. 0 can be in the spectrum without being an eigenvalue. And then finally, sigma of T is compact. As I mentioned in the last part, it's at most countable. That's because we can union up these finite sets over a countable number of R's. And it also has at most one limit point, which is 0 itself. So it's a fairly well-behaved set, the spectrum, if we have a compact operator. Yeah, so I guess that's about as nice of a behavior as you could probably expect in infinite dimensions, given that that a map can fail to be surjective without failing to be injective, right, in infinite dimensions. So 0 is always going to be special, but yeah. So then that's the end of the sort of Rudin's part of the stuff, and I thought it'd be interesting to go through an example here at the end. So I took an example of an operator that's not compact, and I'm going to show why it's not compact. It's actually quite nice to use some of the results from this chapter. So we're going to look at L2, a little L2, which is the sequence space of sequences which are norm summable. And we'll just look at the right shift operator. So we take a sequence and we shift it to the right by 1 and put a 0 in the first slot. I'm sure this is very familiar as an example from where we studied Hilbert spaces. T is obviously a linear map, and you can see it's an isometry because we have the same set of x's. We just move them over by 1, so the norm's going to be the same after shifting. Isometry means that it's both bounded and it's injective, but it's obviously not surjective because the image has to have a 0 in the first slot, whereas that's not true of all of L2. If we had an eigenvalue, so if tx equaled lambda x for some lambda, then we've got lambda x equals t of x, which is this shifted version of x. And then you go through element by element and show that whether lambda is 0 or not, this forces the original sequence to be the 0 sequence. And since we don't allow 0 to be an eigenvector, this says that lambda is not an eigenvalue. So this operator has no eigenvalues, which is also different from the the finite dimensional case. You can pretty easily check that the adjoint in the Banach space sense and in the Hilbert space sense is the left shift operator, which says take the sequence and shift it to the left by 1, dropping the first element. I'm not going to go through the proof of that, but it's fairly straightforward. And if we right shift and then left shift, so we right shift, it means we insert a 0. Left shift, we can get back the original sequence because we haven't lost anything. So T first right shifting and then left shifting gets back the identity. But if you go the other way, if you first left shift, then you lose a first element. So then if you right shift, you don't get back the identity. You've got now a 0 in the first slot. In fact, since T is not surjective, T is the, wait, which one's T? Yeah, T is not surjective. That's the right shift operator. The first element's always a 0, so it doesn't hit all of L2. And since it's not surjective, it can't have any right inverse. So certainly, you would not expect T star to be a right inverse. You can check, and I actually think I added a proof on the last page, which I'll go through briefly. The closed unit ball in L2 is not compact, and so the identity map, which would just map the closed unit ball to the closed unit ball, cannot be a compact operator because the image of the closed unit ball has to be compact in order for an operator to be compact. So the identity map is not compact. And then we have to use this cool theorem, which we stated before. If we have a pair of operators, S and T, then if either one of them is compact, then their product, which is their composition, is also compact. Well, we can apply that here. T star T equals I. I is not compact, and that says, well, neither T star nor T can be compact, because if either one was, then so would the product be, and I would be compact. That's a really slick and easy way to see that these are not compact operators. You can also show, and I didn't go through the proof of this here because it's a little bit more involved, but it's not super hard, that the spectrum of T and the spectrum of T star, it turns out these spectrums are always equal, by the way, for general T and T star in Banach spaces. They're both equal, and they both equal the closed unit ball in C. So it's a set of all lambdas with magnitude less than or equal to 1. So here we have a super failure of this. What we had with compact operators is that sigma of T could at most have 1 point that's not an eigenvalue, namely 0. Well, here we've got an example of a non-compact operator that has no eigenvalues at all, and its sigma of T is the whole closed unit ball of C. So it's got an uncountable number of spectrum values. And that's another way to see that T is not compact, by the way. We had this theorem here, which says that if sigma of T is, if T is compact, then sigma of T is at most countable. And here we've got an uncountable sigma of T. So by two different ways, we show that this is definitely not a compact operator. And we saw that T star is not either, because if it was, then I would be compact, which it's not. So both left shift and right shift are not compact. And then just for completeness, I do show that the closed unit ball in L2 is not compact. You guys have probably seen this before, but it's fun to go through. If you define a sequence in L2 that is just the it's the sequence. It's all zeros except 1 in the nth slot. It's easier to say it than to read the notation. Then the norm of each of those xn's is obviously 1 because it's only got a single 1 and zeros everywhere else. So you take the square of the 1 and the squares of zeros, add them up, you get 1. So xn, this sequence, each element of the sequence is in the closed unit ball. But if we take different n and m, then we'll take their difference. Then you get a 1 in one of the slots and a -1 in another slot and zeros everywhere else. That's going to have norm squared of 2. And so not only is this not, and this is true for any n and m that are distinct. So not only is the sequence itself not Cauchy, but no subsequence can be Cauchy either. and therefore no subsequence can be convergent, and therefore we don't have limit point compactness, and so the closed unit ball is not compact for that reason. So we use the equivalence of limit point compactness and compactness in a metric space. Yeah, so it's kind of fun to use some of the theorems, and I didn't have time to play around with other examples. I did look up a couple of examples of non-trivial compact operators, but there were I didn't find a whole lot of super interesting ones, so I didn't that were easy to explain. So I didn't include any examples. The ones that are easy to explain are also not very interesting, so I didn't go through with them. Anyway, so that concludes the presentation. Hope it was interesting and useful.
Yeah, this was a really cool presentation, actually. Very simple and doesn't have a lot of the at least technical proofs that one would struggle with.
Yeah,
this chapter.
Yeah, I actually found it really useful to sort of just highlight the results without going into too many of the details. It makes it more obvious what exactly did we do in this chapter. Whereas if you read through it and read through all the proofs, they're very there's a lot of not seeing forest for the trees when you're paying attention to all the proofs in this chapter. The proofs they do use the results, but they don't seem super intuitive in a lot of cases. So like they're I call them technical for that reason. They're not they don't really well illuminate why the result is true. At least not until I digest them a lot more, I think. Whereas some of the
Yeah, that makes
in the
sense.
previous chapters that was not so true. The previous chapters the proofs were kind of how you think you would proceed, but here sometimes I wasn't sure how he came up with or whoever came up with the original proofs. They must have done a lot of struggling, but yeah, it's cool to see how it all pulls together, and definitely worth reading the chapter. Even if you don't read all the proofs, it's really useful to read the 4.25 proof. It's quite long, but each step is not too bad, and he uses almost all the results in the whole chapter, as well as Han Banach and the open mapping theorem and several other ones from the previous chapters. So it was really pretty cool.
Yeah, I definitely have to go over it. In general, I think this whenever we like go into at least like new territory, which is essentially this new way to think about the adjoint and operators in general. I think it's natural for the proofs to seem a little bit at least unintuitive and vague. I'm
Yes.
hoping like once we go into like the later chapters, which is at like 10 plus, where these techniques are going to be a bit more obvious.
Yeah, I
In
think
12.
that's been the case so far. Like each chapter, the previous chapter material became clearer because you start using it a lot more, and you start seeing, you start remembering that it's true, and also understanding why it's useful a little bit more as you keep applying it more and more. And I'm sure that'll be true with chapters 10 and later. By the way, on that note, I'm gonna probably have to bail on the subsequent chapters because I decided at the last minute I'm going to take a class this term, so and this is kind of time consuming. I really want to give if I could keep auditing, but I really if I do this, I want to actually spend the time to really learn it right. But it is really time consuming. So I'm
Yeah,
probably going to drop off.
I get that. Yeah, that's okay. I think I've also like have some serious exams coming up soon. I
Yeah,
think
it
we
sounds like
can one thing we
some of you
can
guys
do
are
to go
doing really
around
good
it.
too.
One thing we could do to go around is just to have general meeting of discussion. So take it as I do this in another group where simply every week it's just a meeting where we discuss like the kind of math we learned in general and discuss the topics that we are want to discuss in a group. So if you have the time, at least like per
Yeah, I
week, we
think
can still.
yeah, I think as long as we can schedule it, or if we can be flexible with exactly when it happens, I think for sure, I can
Mhm.
definitely participate in that, and I can like read. I think I have enough bandwidth to at least read like all the statements of all the theorems in the subsequent chapters, and maybe skim a few of the proofs. But I just don't have the time to do the deep dive like I've been trying to
Yeah, I
do.
understand what you mean.
Yeah. Mhm.
That's now at least my goal, like with moving forward, where it's become less of a because like the first four chapters, okay, it makes sense that we had to sit down and really get into them. But moving forward,
Yeah.
I think we can just like chill out. I guess is the word for
Yeah.
it.
Yeah.
All
I
right.
could definitely be on board with that for sure. and then maybe we can talk a little bit about distributions in there too, which is the topic I've been. I know we voted to go the other path, but we could sneak a little distribution content in there anyway. I can read up a
Yeah,
bit and maybe say a few things.
I'd be down for that. It is a cool topic.
Yeah,
Let's
I
see.
learned a little bit in the past, but not. I never really learned much about the whole how it relates to the various weak topologies and topological vector spaces and such. I haven't. We didn't really go through. I think it was kind of tacitly there, but it wasn't really. We didn't really go formally through all that stuff. So it's going to be interesting to see how it sort of meshes with all the stuff we've done in the previous chapters. I think.
Mm-hmm. Yeah, makes sense. I think it would be interesting, especially since it opens the way towards a lot of interesting topics in general, specifically a bit more advanced Fourier analysis for me.
Yeah, for sure. The Fourier transform behaves beautifully on the space of tempered distributions. Like it's a bijection. It's an isometry. Oh, no, sorry, not isometry. It's definitely a bijection. It's not isometry on L2, but so every tempered distribution is the Fourier transform of something, and every tempered distribution has a Fourier transform. So like you gigantically increase the number of things that you can take Fourier transforms of. Like every locally L1 function is a tempered distribution. So like every L1, everything that's either in L1 or fails to be an L1 only because it has a heavy tail is basically Fourier transformable, which is really cool.
Yeah, makes sense.
Yep.
Right. So I guess that would be it for this week. We'll have to schedule our next meeting a bit further than usual because exams and all, sadly.
Mm-hmm. Yep.
But that was a really nice presentation again.
Okay. Yeah. So just let me know in the channel like what when you're proposing to do the next one, and I'll if you